Hello, I'm Dr. Ron England, and I am going to discuss the Tower of Hanoi, the classic computer science problem with you today. And this is one that really sometimes students have a hard time with. Maybe it's an implementation or the coding, but it's the classic recursive example. For those who aren't familiar with the Tower of Hanoi, is the legend of the Tower of Hanoi, but it's simply a game where you have concentric disks that are of varying size, where you try to move the disks from one post to another, with never putting a disk that's larger on top of a disk that's smaller. And this has been a classic example in computer science just because there's a classic implementation that is done with recursive function calls. And this is that implementation right here. So the way this works is, this is a function. Disk is an n, it's the number of disks, and 3, it has source, destination, auxiliary, and those are just 3 stacks. A stack is a simple, for those people who are watching this, you should understand the concept of a stack. But a stack is something simply that you can put something on the top and take something off. And the way the algorithm works is a classic algorithm because it's like every other recursive algorithm. For every recursive algorithm, you must have a exit condition, something that gets you out of the recursive algorithm. Otherwise, it would just continue to call itself forever. And in this case, the exit condition is simple. If disk, which is the n, the number of disks, is equal to 1, all it's going to do is move a disk from source to destination. So it's going to take a disk off of one and move it to the other. If not, it's not equal to 1, it's going to recursively call itself. So it's going to call itself, but if you notice, 2 things happen. One, the number passed is decremented by 1, and the order of the actual stacks is changed. Now this recursive function, this recursive algorithm actually calls itself twice within the algorithm. So you'll have a call to the function once, then you're going to move a disk, and then you have a call a second time, and in this second time it actually changes the order of the stacks again. Now what this will do is it will actually implement the concept of moving the disks in such a way so that no disk is larger than the disk that it lands on top of. We're not going to discuss the actual ins and outs of this algorithm. What we're going to do is we're going to look at the implementation in JavaScript. So if I look at this implementation in JavaScript, this is just a standard JavaScript implementation of this. If I say calculate number of moves, which is what my goal is here, you can see that I have the original stack before, and the original stack, the destination stack before, and then them afterwards, and it took 31 moves to do it. Now, you're just going to have to trust that I did that. Well, not really, because I'm going to show you the code that I used to do that. Now, first code that I'm going to show you is up here, is just where's the entry and the button. If you look at the button, I call a function called run. So let's look at run. Well, run does one thing. It first instantiates the 3 stacks, A, B, and C. We're doing this with real stacks. You need to not just pretend to move the disks. You need to move the disks. And to move the disks, you have to use real stacks. Then what I do is I get the number from the user of how many you're going to put on top of the first stack, and I fill the first stack by simply calling the push function of the stack with a decrementing number. And then I output, the output that you saw is right here, and then of course I have the output afterwards, but I'm going to call that recursive function run Hanoi. Well, let's go down here and let's look at that Hanoi function. It's a good function to look at, and I'm going to explain some of the things that I do. It's going to look exactly like that function you saw in pseudocode. Z is going to be the number that's passed over to it. It's a number. And the exit condition is if Z is 1, you're going to move. Now, I do have a num++ because I'm counting how many moves I made. And num is just a global variable. Okay, if Z is not equal to 1, I make the recursive call with the Z minus 1, moving the orders of the stacks. I then move and I increment num, and then the second call to run Hanoi, just like in the pseudocode. Now, there's one thing that I did show here that I did do, which is actually worth looking at. And let me scrunch this down just a touch, because I think I can show it to you a little bit better if I move it up. Okay, I abstracted the function move to an abstract function, move. And the reason I did that was because my implementation of a stack is a traditional implementation of a stack. I will prove to you that I implemented it because here it is. Var stack equals function. It's a JavaScript object that I created that implements push and pop and has node pointers. That, of course, is the subject of a totally different lecture. But I do cover that in another lecture if you really need to know how to do that. The move simply does take the source stack, pop it, take the contents of the pop, and push it on to B. Okay, that's moving from A to B. Now, if you put all this together correctly, okay, you can easily then see, have this wonderful stack that's right here and see how it works. Okay, we can do this now with, let's say, 6. Let me go ahead and click the run over here, run. I'm going to sort of blank everything out. And now I'll run it with 6 here, moving some things around. And you can see it, boom, there it is, and solved. Hopefully this helps you out in the concept of the Tower of Hanoi and also writing good, clean code. Because one of the things I definitely see students do is way overcomplicate problems. They're not that hard many times to solve. You just got to tackle the problem by tackling the problem, not just throwing code on a page. Hope that helps. Good programming. See you later. Bye.